In this video, I'm going to describe the mathematics of the Hardy-Weinberg Equilibrium, which is a description of generation by generation changes in the allele frequency in a population. So I'll start off with just a small population of individuals. So we're going to have 4 of them. And these 4 individuals have different phenotypes, meaning they look different. Some of them have big ears, some of them have little ears, and some of them have no ears. So this is what we call the phenotype. And if you look under the hood, you'll see that each of them have inherited a different allele. So that's a different version of a gene. So each of these are alleles. And obviously this is a gene that encodes for some kind of ear development. And so each of these are alleles, and this one, let's say, has AA, and so does the other one with big ears. The one with intermediate ears or small ears has AB, and the one with no ears has BB. So, and this whole thing here is what we call the genotype. So you have a genotype consisting of 2 alleles, well, really a whole collection, but let's say the genome is just restricted to this one gene. So the entire organism is ears or no ears, I guess. And you can either have an AA, an AB, or a BB. Okay, so we define the frequency of the allele as being the number of alleles divided by the number of alleles of a particular type, let's say A, divided by the total number possible. So there's 8 possible alleles in this population, and the one that we're looking at has 5 A's, and so 5 out of 8 of them are A's, and we'll call this in our calculations below, I'm going to refer to this as P. And then F1 of B is going to be the rest of them, 3 out of 8, and those are 3 alleles B, B, and B out of 8 are B's. Okay, and I'm going to call that one Q, and now clearly we have to have that P plus Q is equal to 1. Now the subscript here, 1, I'm referring to the first generation in that of that population. Okay, so we can also talk about the frequency in the first generation of the genotype AA, and in this case, half of them have AAs, a quarter of them will have AB, and another quarter of them will have BB. Okay, so imagine this population is larger and large enough that they're well mixed, and we're also going to assume that nobody has specific A or B biases. Nobody chooses their mate based on the phenotype, so we call that non-assortative mating. And when that's the case, what we can do is write down what's called the Punnett Square for this population, and that is going to look like this, a square, obviously, hence the name. And what we put in it are, here's mom and here's dad, and these are the alleles that mom might give you and the alleles that dad might give you, A, B, A, and B. And so if mom and dad both give you an A, the chance of that happening is going to depend on, in general, I mean, you're just getting, without knowing specifically who mom or dad are, you're just getting the alleles sampled randomly from the population, and there's a P probability of getting an A, so there's going to be a P squared probability of getting 2 A's, and that's the probability of getting AA. So what about the probability of getting A from dad and B from mom? Well, there's going to be a P times Q, and that's specifically the probability of getting A from mom and B from dad. You'll also have a P times Q for the probability of getting B from dad, B from dad and A from mom, and then a Q squared probability of getting B from both. So that is our Punnett square, and what that lets us do is it lets us write down the next generation, F2, of each of the genotypes. So the F2 is going to be given exactly by the entries in these squares. So the probability or the frequency of seeing AAs is going to be p squared. The frequency of seeing ABs, well, some of those ABs will have gotten their A from mom and some from dad, so we have to take into account both this square here and this square here, and we get 2 times PQ. And then F2 of BB, similar to the first one, is just now going to be Q squared. And you'll notice that, so I had already pointed out that P plus Q is equal to 1, and you'll notice if we square that, P plus Q squared is P squared plus 2PQ plus Q squared, which is also equal to 1, because 1 squared is 1. And that tells you that the the genotype frequencies also still adds up to 1, which is a good thing because that would be our entire population. Okay, that would mean that, if not, there would be some other phenotype or genotype that had been sneaking in here. Okay, so once we know what the population, the genotype frequencies are for the population, now we can write down what F2 of A, what is the allele frequency, and you can think of this as, let's say you had 100 people in your population, then you would have 100 times p squared AAs, and you would have 100 times 2, so 200 times PQ ABs, and so on. And then if you want to know what the frequency is, you divide by the total population size. So divide by 100 and divide by 100. And that would cancel your hundreds, and this would cancel your hundreds, leaving the 2. And so what we get then is the frequency of the allele A is going to be p squared, coming from these ones here, 2 alleles, but then there's 2 slots that they could be in, so you divide by 2. Or said another way, if you have 100 people, you would have 200 times p squared alleles, and you'd have to divide by 200 possible alleles in your population. And so those 2's are going to cancel in a moment, but let's leave them in for now. And then similarly, we have 2pq for the frequency of ABs, and then we divide by 2 also again because there's 2 alleles per person. And so the total here comes out to 2p times p plus q, and p plus q is just 1, so this is just p. So F2 of A is going to be P, and F2 of B will be, by a very similar calculation, will be Q. Now this is kind of a remarkable thing. We had an allele frequency initially, and we distributed it in a random way in the population, not according to reproduction. I just wrote them down in some particular way. I said, oh yeah, I've got 2 big ears, 1 small ear, and 1 no ears. So we ended up with a half, a quarter, and a quarter. Now there's no reason for those numbers to be anything in particular on my invented generation, but as soon as this generation, the F1 generation, reproduces, if they do so non-assortatively, we get on the next generation exactly the same allele frequencies, and we get these special genotype frequencies. And these genotype frequencies are what we call the Hardy-Weinberg Equilibrium. Because if you go to F3, you'll see that you get p squared, 2pq, and q squared again. And you can see that very easily because little f2 was p and q, just like f1 was, which means those are going to determine f3 exactly the same way f1 determined the capital F2 generation. And so the Hardy-Weinberg Equilibrium, is this remarkable equilibrium that establishes itself immediately in one generation. That's assuming you have a large enough population and you don't mind a little bit of noise from the randomness of mating choice. Okay, so that's the discrete case. In a separate video, I will go through and describe what happens when you generalize this to a continuous reproductive phenomenon. In other words, you don't have discrete generations, but you have individuals or couples reproducing at whatever time, and so we describe it with a continuous variable instead of this F1, F2 description.